Introduction to Linear Transformation. Good day everyone. The assigned topic in my group is all about Introduction to Linear Transformation. So before images and free images of functions. So in this chapter we will learn about the functions that map a vector space V into a vector space. Students will be able to this type of function is denoted by T is mapped. Good day everyone. The assigned topic in my group is all about Introduction to Linear Transformation. So before map from the domain set of lesson our image. So before we proceed to our lesson, our discussion, we have here an objective. So at the end of this lesson, students will be able to define linear transformation, show that a function is a linear transformation, show that a function is a linear transformation, and lastly, understand the concept of the composition of linear transformation, including how to multiply matrices to represent the composition of linear transformation. Images and free images of functions. So in this chapter, we will learn about the functions that map a vector space V into a vector space W. This type of function is denoted by T is mapped from the domain set of V or the codomain set of W. So as you can see in the figure below, so the standard function terminology is used for such functions. For instance, V is called the domain of T and T is called codomain of T. So if vector V is in the vector space domain V and the vectors W is in the codomain vector space W, such that T of V is equals to vectors W, and it is called the image of vectors V under V. So the set of all images of vectors in V is the range of T, and the set of all vectors V and domain vectors V such that T of V is equals to W, or what we call the pre-image of W, that we can see in the figure in the presentation. So T is mapped from the domain set of V to codomain set W. So it represents that a function named T that takes input from the set of V and produces output in the set of W. So it indicates that the domain and the codomain of the function, providing information about the set of input values and set of possible output values of the function. So we have here an example of image and the pre-image of a function. So example number 1, a function from R2 into R2. So for any vector V1, V2 in R2 defined by T is mapped from R2 to R2 by T V of 1 V2 is equals to V1 minus V2 V1 plus 2V2. So ayun yung formula na gagamitin natin para mahanap natin yung image. So we have here an example, letter A. Find the image of V is V equals negative 1 and 2. So solution natin dyan, makikita natin sa presentation. So for V is equals to negative 1 and 2, we have T equals V1 natin is negative 1 and our V2 is 2. So substitute lang natin. So V1 is negative 1, negative V2. So gagawin natin negative yung V2. So since positive si 2, gawin natin negative. So negative 2. So V1 natin is negative 1 plus 2 times V2. Our V2 is 2. So, negative 1, negative 2 is negative 3. So, negative 1 plus 2 times 2 is negative 1 plus 4 is 3. So, our image for vectors b, negative 1, and 2 is equals to negative 3 and 3. Negative 3 and 3 is our image. So, letter B. So, if b is equals to 0 and 0, then the image of our function is 0, 0 din. Since minultiply natin dun sa part na si b2 is 0. So, pagiging 0 talaga siya. So, ang image niya is 0 pa din. So, letter C. If t of b is equals to b1 minus b2, b1 plus 2b2 is equals to negative 1, 11. Then, b1 is equals to b2 equals to negative 1. b1 plus 2b2 is equals to 11. So, hinahanap dito is the pre-image ng vectors w na negative 1 and 11. So, the pre-image ng negative 1 and 11 is 3 and 4. So, the system of equation has the unique solution b1, 3, and b2 is equals to 4. So, the pre-image of negative 1 and 11 is the set in R2 consisting of the single vectors 3 and 4. So, reminder for vectors b is equals to b1, b2, and bn, and so on and so forth in Rn. It would be technically correct to use double parenthesis to denote t of b, as t of b is equals to t, b1, b2, b3, b4, and so on and so forth. So, for convenience, however, drop one set of parentheses to produce t of b is equals to t, b sub 1, b sub 2, and so on and so forth. So, makikita nyo siya dyan sa presentation natin para mas madali, masusundan nyo siya. So, what is linear transformation? Linear transformation is this centers on functions that map one vector space into another. So, that preserve the operation of vector addition and scalar multiplication. Or, it is also known as a linear map or linear operator is a function that preserves a certain algebraic properties of vector spaces. Specifically, a function of t is mapped from b to w is called a linear transformation if it satisfies the following two properties for all vectors u and the b in the domain vector space v and all scalar constant c. So, we have here two properties para masatisfy kung linear transformation ba siya. One is the vector addition and two is the scalar multiplication. One is vector addition, t, function of t, u plus b is equals to t of u plus t of b. So, this property states that the transformation of the sum of two vectors is equal to the sum of the transformation of the individual vectors. In other words, the function preserves vector addition. So, may example tayo dyan mamaya sa next slide. So, number 2 is scalar multiplication. So, t cu is equals to ct of u. So, this property states that the transformation of scalar multiple of a vector is equal to the scalar multiple of the transformation of the vector. So, in other words, the function preserves scalar multiplication. Nabanggit ko naman kanina yung about sa vector addition and scalar multiplication. So, ito yung formula niya. So, addition in vector b is t of u plus b. Ang addition in w is t of u plus t of b. Sa scalar multiplication ng b naman is t's of c and u, and sa scalar multiplication naman ng w is ct's of u. So, we have here an example number 2, or we're going to verify a linear transformation from R2 into R2. So show that the function given in example 1 is a linear transformation from R2 in R2. So given dun sa number 1, need nating i-verify yung linear transformation. So t is of v1 and v2 is equals to v1 minus v2 plus 2v2. So sa next presentation, nandun yung solution. So we have here a solution. To show that a function t is a linear transformation, we must show that it preserves vector addition and scalar multiplication. So sabi doon, ang linear transformation daw is malalaman natin if masatisfy niya yung vector addition and scalar multiplication. If masatisfy niya yung dalawang properties na yun, then we can say that a function is a linear transformation. So to do this, let v equals to v1 and v2, and u is equals to u1 and u2. Be vectors in R2, and let c be any real number. Then, using the properties of vector addition and scalar multiplication, we have the following two statements. So, because u plus b equals to u1, u2 plus b1 and b2 equals to u1 plus b1, u2 plus b2. So, we have t u plus b is equals to u1 plus b1, u2 plus b2, as you can see in the presentation. So, equals to u1 plus b1 minus u2 plus b2, u1 plus b1 plus 2u2 plus b2. So, i-multiply dito sa part na to yung 2u2 plus b2. Next is u1 minus 2u2 plus b1 minus b2, u2 plus 2u2 plus b1 2b2, u1 minus u2, u1 plus 2u2 plus b1 minus b2, b1 plus 2v2. So, equals to t of u plus t of b. So, nasatisfy niya yung vector addition. Next is the scalar multiplication. So, because cu is equals to c u of 1, u2 equals to c u1 and c u2, we have t of cu equals to t of cu1 and cu2. So, cu1 minus cu2, cu2 plus 2cu2. So, is equals to c quantity of u minus 2u2 to u1 plus 2u2 equals to c t of u. So, we can say that t is a linear transformation based on our solution. So, since nasatisfy niya yung dalawa, nasasabi natin linear transformation siya. Kapag hindi niya nasatisfy yung dalawa, or isa lang ang nasatisfy niya, kunwari, nasatisfy niya yung vector addition and hindi niya nasatisfy yung scalar multiplication, we can say that it is not a linear transformation. Basta masatisfy niya yung dalawa, linear transformation siya. So, always remember that a linear transformation, t is mapped from codomain vectors b space. A linear transformation is mapped from codomain vector space b to vector space b from a vector space into itself, as an example in number 2, or we can call it linear operator. Most of the common functions studied in calculus are not linear transformation. So, in example number 3, some functions that are not linear transformation. So, example of this is the f of x is equals to sine of x is not a linear transformation from R into R. Dahil na din, in general, ang sine of x of 1 plus x of 2 is not equals to sine x of 1 plus sine x of 2. For instance, sine pi over 2 plus pi over 3 is not equals to sine pi over 2 plus sine pi over 3. So, example letter B, f of x is equals to x squared is hindi din siya linear transformation from R into R dahil na din sa x of 1 plus the quantity of x of 1 plus x of 2 is not equals to x of 1 squared plus x of 2 squared. For instance, or for example, the quantity of 1 plus 2 squared is not equal to 1 squared plus 2 squared. So, example letter C, function of x is equals to x plus 1 is not also a linear transformation from R into R because f of x of 1 plus x of 2 is equals to x of 1 plus x of 2 plus 1, whereas f of x of 1 plus f of x of 2 is equals to x of 1 plus 1 plus x of 2 plus 1 is equals to x of 1 plus x of 2 plus 2. So, f of x of 1 plus x of 2 is not equals to f of x of 1 plus f of x of 2. So, two simple linear transformation are the zero transformation and the identity transformation, which are defined as follows. So, t of p is equal to 0 for all p, or yun yung tinatawag na zero transformation. Yung t is mapped from b to w, and t of p is equals to vector b for all vectors b. Yun yung tinatawag na identity transformation, o yung t is mapped from b vectors b from B to B. So, the verification of the linearity of these two transformations are left as an exercise 77. So, no need na. So, note that the linear transformation in example 1 has the property that the zero vector map to itself. So, that is 0, t of 0 is equal to 0, or yun yung tinatawag na zero transformation or the identity zero transformation. So, in example number 1b, this property is true for all linear transformation as stated in the first property of the following theorem. So, remember that the function in example 3c suggests two uses of the term linear. So, the function f of x is equals to x plus 1 is called the linear function because it is a graph of a line. So, it is not a linear transformation from the vector space R into R. However, because it preserves neither vector addition nor scalar multiplication.
Okay, so we have here theorem 6.1, which is all about the properties of linear transformation. So we have four properties, and we are going to prove each of it. So to prove our first property, we have to go back to Michel's discussion about the second property under the definition of linear transformation, which is the TCU or scalar multiplication in B is equals to CPU or the scalar multiplication in W, wherein we say that T preserves scalar multiplication. So, if T is a linear transformation, then T0 is equals to 0. So, how is that? So, we can see on the screen the solution and how we derive with that property, and how we derive that the property is true. So, we have, or we can see here that the linear transformation T ng 0 is equals to T0 vector B, is equals to 0, t vector b is equals to 0, noting that 0 vector b is equals to 0. Next property we have is the linear transformation of the negative vector b is equals to negative linear transformation ng vector b. So to prove this, t times or the linear transformation of the negative vector b is equals to linear transformation negative 1 times the vector b, since we have to remember that negative vector is equals to negative 1 times the vector itself, and that would be equals to negative 1 times the vector is equals to negative 1 times the linear transformation of the vector b. So after that, that will be equals to negative linear transformation of the vector b, since we follow that the negative b or the negative vector is equals to negative 1 times b. Okay, so for the third property, we have here the linear transformation of u minus b is equals to t times the vector u plus negative 1 times the vector b, since u minus b is equals to u plus negative vector b. So, sinubstitute lang natin siya doon, and then that would be equals to tu plus negative 1 linear transformation of the vector b, and that is also equals to tu or the linear transformation of u minus tb. Therefore, we arrive with this kind of property, with this kind of solution, so we can say that this property is true. Okay, so for the fourth property, we use induction on n. For n is equals to 1, we have t c1b1 is equals to c1 tb1 by property 2 of the definition of the linear transformation that is discussed by Michelle. So now for n is equals to 2 naman, by the second property under the definition of linear transformation ulit, we have t c1b1 plus c2b2 is equals to t c1b1 plus t c2b2, and that is equals to c1 t b1 plus c2 t b2. So for is proved for n is equals to 2, or so this property is proved for n is equals to 2. So now we can assume that this formula 4 is valid for n minus 1 vectors and prove it for n. So we have now tc1b1 plus C2B2 plus so on and so forth plus CNBN, and that will be equals to T C1B1 plus C2B2 plus so on plus Cn minus 1Bn minus 1 plus T Cnbn is equals to C1T B1 plus C2T B2 plus so on, and then plus Cn minus 1T times Bn minus 1 plus Cnt Bn. So thus this property is true. Okay, so for our example number 4, the linear transformation and basis. So let linear transformation of R3 into R3 be a transformation such that T100 is equals to 2 negative 1 4, T010 is equals to 1 5 negative 2, and T001 is equals to 0 3 1. So we have to find linear transformation of 2 3 and negative 2. So we have our solution on the screen. So because 2 3 and negative 2 is equals to 2 times 100 plus 0 times 010 minus 2 times 001. You can use property 4 of theorem 6.1 to write. So, di ba, whenever we multiply or add vectors, hindi natin siya agad minumultiply or hindi natin direct na dinidistribute to multiply the number. So, we can write it this way. So, t 2 3 negative 2 is equals to 2t 100 plus 3t 010 minus 2t 001. Now, yung mga t 100 ganyan, and then yung t 010 and then t001, we can substitute it with its actual value, which is also given naman. So, like for example, yung value ng T100 natin is 2, negative 1, and 4. And then, ang value naman ng T010 natin is 1, 5, negative 2. And then, our value for T001 is 031. We can write it that way. And then we can now distribute each number or multiply each number. So we multiply natin yung number on the outer side of the parentheses doon sa numbers on the inside. So that will be 2 times 2 is equals to 4. 2 times negative 1 is negative 2. 2 times 4 is equals to 8. Plus, copy the plus sign. 3 times 1 is 3. 3 times 5 is 15. And 3 times negative 2 is negative 6. Copy the sign minus. 2 times 0 is 0. 2 times 3 is 6. And 2 times 1 is 2. So, at this point, pwede natin siya i-add. But we should not add it ng 4, negative 2, 4 plus 3, 15, negative 2. So, hindi natin siya ganun i-add. So, i-add natin siya by number. So, yung unang number muna, mga unang number muna. So, that are 4, 3, and 0. So, 4, 3, and 0, i-add natin siya. That would be equals to 7. Next numbers is negative 2, 15, and 6. So that would be equals to 7 as well. Next, for our last numbers, that will be 8 plus negative 6 minus 2. So that would be 0. So that is how we solve for its linear transformation. Okay. For number 5, a linear transformation defined by matrix. So define the function linear transformation R2 into R3 as follows. So linear transformation ng vector is equals to the augmented ng vector. So that would be 3, 0, 2, 1, negative 1, and negative 2 times yung vectors natin, which is V1 and V2. So we have to find TV where V is equals to 2 and negative 1. So our solution can be seen on the screen naman po. So since we already have the value of our vectors, which is v1 is equals to 2 and our v2 is equals to negative 1, we will come up with tv is equals to ab is equals to 3, 0, 2, 1, negative 1, negative 2, tapos yung vectors in R2, which is yung 2 and negative 1 nga. So we will come up with an answer 6, 3, and 0 as our vector in R3. So how did we come up with that answer? So alam naman natin, in adding vectors, we have to add it row by column. So we have to multiply it pala by row by column and then add it. So just like this, 3 times 2 plus 0 times negative 1. So 3 times 2 is 6 plus 0 times negative 1 is equals to 0. So 6 plus 0 is equals to 6. And then 2 times 2 plus 1 times negative 1. So 2 times 2 is equals to 4 plus 1 times negative 1 is negative 1. So when we add 4 and negative 1, we will come up with number 3 with an answer of 3. And then for the last one is negative 1 times positive 2 plus negative 2 times negative 1. So negative 1 times positive 2, that would be negative 2 plus negative 2 times negative 1, that would be positive 2. So negative 2 plus positive 2 is equals to 0. So now we have the linear transformation ng 2, negative 1. So that is equals to 6, 3, and 0.
So now let's talk about the linear transformation given by a matrix. Let A be an M times X matrix. The function T defined by T of B equals to AB is a linear transformation from R raised to N into R raised to M. In order to confirm to matrix multiplication with an N times N matrix, N times 1 matrices represents the vectors in R raised to N, and M times 1 matrices represents the vectors in R raised to M. Be sure you see that an M times N matrix, A defines the linear transformation from R raised to N into R raised to M. So for this example, consider the linear transformation T is to R raised to N to R raised to M defined by T of B equals to AB. Find the dimension of R raised to N and R raised to M for the linear transformation represented by each matrix. For the first one, the solution, because of the size of this matrix, is 3 by 3. It defines the linear transformation from R cubed into R cubed. The second one, because the size of this matrix is 3 by 2, it defines the transformation from R squared into R cubed. And the last one, because the size of this matrix is 2 by 4, it defines the linear transformation from r raised to 4th power into r squared. For this example, show that the linear transformation t r squared to r squared represented by the matrix has the property that it rotates every vector in r squared counterclockwise about the origin through the angle 0. So for the solution, you know that t is the linear transformation to show that it rotates every vector in r squared counterclockwise through the angle. Let v equals to the quantity of x and y be a vector in r squared. Using popular coordinates, you can write v as v equals to the quantity of x and y is equals to r cosine a or r sine a, where r is the length of v and a is the angle from the positive x-axis counterclockwise to the vector v. Now applying the linear transformation t to v produces, so the vector t of v has the same length as v. Furthermore, because of the angle from the positive x-axis to t of v is the vector result from rotating the vector v counterclockwise through the angle as shown in the figure. So for this example, the linear transformation t to r cube represented by is called the projection in r cube. If v equals to the quantity x, y, z is a vector in r cube, then t of v equals to the quantity of x, y, 0. In other words, t maps every vector in r cube to its orthogonal projection in the xy plane as shown in the figure. So far, only in the linear transformation from r to the raise n into r into the raise of n, or from the r raised to n into r raised to n have been discussed. The remainder of this section considered some linear transformation involving vector spaces other than r raised to n. For this example, let t to the m and n into m and n be the function that maps an m times n matrix A to its transpose, that is t of a to the raise of t. Show that t is the linear transformation. Solution: let a and b n times n matrices. From theorem 2.6, you have t of a plus b equals to the quantity of a plus b raised to the power of t equals to a raised to t plus b raised to t equals to t times a plus t times b, and t times ca equals to the quantity of c and a raised to t is equals to c times a raised to t equals to c t times a. So t is the linear transformation from mn into m and m. For this example, let C be the set of all functions whose derivative are continuous on a and b. Show the differential operator d defines a linear transformation from c times a and b into c times a and b. Using operator notation, you can write d of f equals to d over dx times f, where f is in the c times ab. To show that d is the linear transformation, you must use calculus. specifically because the derivative of the sum of two differential function is equals to the sum of their derivatives. You have d of f plus g equals to d over dx times f plus g equals to d over dx times f plus d over dx times g is equals to d of f d times f plus d times g, where the g is also in c times b. Similarly, because the derivative of scalar multiple of the differentiable function is equals to the scalar multiple of derivative, because the sum of two continuous function is continuous, and because the scalar multiple of a continuous function is continuous, d of x is the linear transformation from c to ab into c times ab. The linear transformation dx example is called the differential operator for the polynomials. The differential operator is the linear transformation from Pn into Pn minus 1, because the derivative of the polynomial function of degree n is a polynomial function of the degree n minus 1. That is, the next example describes the linear transformation from the vector space of the polynomial function P into the vector space of the real numbers R.